Today our CITA seminar speaker is Dr. Charlotte Welker. She is a postdoc fellow in McMaster University. Before joining McMaster University, she was a postdoc fellow in University of Western Australia, and she did her PhD in IAP in France. She is working on the galaxy formation and large-scale structure. Today, she is going to tell us the galaxy kinematics in the cosmic web.
Hello, everyone. So thank you for the introduction and for the opportunity to give a seminar here. So yes, today I'm going to focus on galaxy kinematics in the cosmic web, as in how galaxy kinematics can be influenced by the cosmic web. And I will be explaining that from simulation on one side and integral field spectroscopy on the other side. So let's start. I'm pretty sure everyone knows about the cosmic web in this room. By cosmic web, I mean this intricate network that you can see from the galaxy field in any spectroscopic surveys. So this network that arises from quasi-linear aspherical collapse, and that is basically a set of voids, very underdense regions, segmented by walls of slightly higher densities, themselves delineated by filaments of high density, branching into nodes of even higher density. So the question we've been asking with my collaborators over the last decade, well, for me at least, is whether the galaxy properties can be correlated to this anisotropic density field, but not only to the density, but also to the anisotropic aspect of it. So another way to put that is the angular momentum a hidden variable to understand the distribution of galaxies in the structures and how their properties evolve in the structure. An even narrower view of that is, can we relate the kinematics of galaxies to that of the cosmic web? So by kinematics of the cosmic web, I mean the cosmic flows, the geometry of the cosmic flows directly influenced by this anisotropic distribution of matter. So here you have an example from a gadget simulation of a filament that is pointing towards you, segmented by 4 walls, segmenting themselves big voids. And you have a few example tracer particles to show you the flow. So by cosmic flows, we mean the fact that matter flows from void to walls, then from walls to filaments, and from filaments to nodes, which in the process generates regions of very high vorticity in the vicinity of the filament, where most of the shell crossing happen. In particular, what you can see is that statistically, around a given filament, you tend to form 4 quadrants of vorticity roughly aligned with the filament and with alternate polarity. That means if one is pointing like this and the other one is pointing like this, the vorticity field. So you have those high vorticity quadrants right around the filament, and that happen to be the areas where most of the galaxies are born. And then, after being born in these regions, they will progressively migrate toward walls and filaments, and then migrate along the filament towards the nodes. So the question I'm actually asking is, those coherent flows, do they have any impact at all on the resulting angular momentum and on the resulting kinematics of galaxy? Which, as you can see, could make sense, because you have coherent flows, so you would expect angular momentum rich accretion in these regions, but then along the filament, you would expect a lot more interactions along the filament itself, so in another direction, so you could expect different outcomes for galaxies. This has been investigated quite a lot in the last 2 decades mostly. First, for halos, there are many more papers that are relevant to the subject. I'll just highlight a few ones. So first for halos and then later on for galaxies. And the claim is very simple. The claim is that galaxies, or halos, transition from a spin aligned to their nearby filament at low mass to a spin orthogonal to their nearby filament at higher mass. So there is transition from aligned to orthogonal as you grow in mass. Would it be halo mass or stellar mass? One of the simulation we identified the trend in for galaxies was in the Horizon AGN simulation, a big 100 megaparsec scale hydrodynamical run with a lot of subgrid physics and kiloparsec resolution. And the way we identified that is by looking at the average angle of the angular momentum of galaxies with the orientation of their nearby filament. And if you look at the absolute cosine of it, and you look at the PDF of this cosine, then you realize that if you focus on very low mass, low stellar mass, in that case galaxies, you tend to have an excess probability at higher values, which means an excess of alignment to the filament. While at much higher mass, you see the opposite trend, an excess of orthogonal orientation and depletion of aligned orientation. So you kind of see this transition for galaxies from a simulation. So here's a sketch to recap the claim. So this is one of the main impacts that has been identified in simulation from the cosmic web to galaxies. And because it can't just be explained by a density effect, it is considered one of the main topics in the area of interaction between cosmic web and galaxy evolution. But as you can see, the effect, for galaxies at least, is still pretty small. If you look at the studies with halos, the signal with halo mass is usually much, much stronger for the dark matter. But for galaxies, it remains quite faint. And I would say from the point of observations, even very elusive. So just to recap, how you expect this to happen? Well, from the theoretical side of things, the scenario is quite well constrained at this point, I would say. There is two sides of the coin. First, you can see things from an Eulerian point of view and focus at the form of the accretion into the galaxy. So usually the scenario goes like this. At low mass, the galaxy grows from diffuse accretion within a vorticity quadrant. So it acquires angular momentum aligned with the filament because the vorticity is on average aligned with the filament in those regions. And then as it grows in mass, it comes closer to the spine of the filament. Quadrant of vorticities with opposite polarity overlap. So you don't really have this effect anymore. But on the other side, you get a lot more mergers happening along the spine of the filament. And during those mergers, orbital angular momentum is transferred to the intrinsic angular momentum of the remnant, progressively explaining an orthogonal orientation. So you have diffuse accretion at low mass, mergers along the spine of the filament at high mass, explaining this dichotomy. That's the Eulerian view. For those of you who like a even more theoretical aspect, more analytical at least, there is also a Lagrangian way of explaining things, that is going just in the initial conditions and try to infer whether you can recover that. So of course that will be for dark matter halos only. But the claim is that you can actually explain this from a tidal Toki theory, which relates the angular momentum acquired by a patch of matter to correlations between its inertial tensor, so its local shape basically, and its tidal tensor, so the tidal field it experiences. This one probing seemingly larger scales than this one. So the idea is that if you're near a filament or a proto-filament, because you're in the initial conditions, then you're near a specific type of saddle point, And your inertial and tidal tensors are correlated due to this environment. They're not completely random, which was the simple assumption that was done in previous studies. So in 2015, Sandrine Codis, who was at CITA for a while, so some of you might know her, she extended tidal Toki theories, taking into account this correlation. And that actually explains the trend. And I'll give you a simple example here. So here is a cross-section of a filament, right? You have the spine of the filament here, walls here, and more voidish regions in this area. So what happened for a proto-halo that would be born here? Well, you expect its inertial tensor to be sensitive mostly to the wall over density, so to be a shape to be most likely oriented toward the wall. But if you look at the tidal tensor for this same proto-halo, it probes slightly larger scales, so it is sensitive to the walls and to the spine of the filament. So it's more like this. And then what tidal Toki theory tells you, it does the Zeldovich boost that the proto-halo will feel tends to realign I and T. So you get something like this. And that's how you get a spin orthogonal aligned to the spine of the filament. And you can do that in every area, and you'll see that you recover the 4 quadrants structure. You can do the same thing using a cross-section of the filament that goes from node to node, so just the spine of the filament. And you can do the same exercise. This time the prominent features are the filament and the node, and you will recover the orthogonal orientation as well. So those two views actually go well together. You have the Lagrangian view that tells you what angular momentum will be acquired by a Lagrangian patch of matter during its evolution in time. And you have the Eulerian view that tells you more about in what type of processes will be involved in this collapse.
I just have a question about the Eulerian view and this picture where I have these things outside of the filaments that are the angular momentum. How do you define that? Is that a scale-dependent thing, and therefore we have a spectrum inside?
For the vorticity, you mean? Yeah. So the vorticity is scale-dependent, and that is the reason of many discrepancies between studies. What you see, however, is that whatever the scale down to all scales that would matter, you would like to define as galaxy environment, that is down to a few hundred parsec. You can compute the vorticity on every scale down to those scales. You still find this aligned structure. Of course, the more you go to lower scale, the more you're actually sensitive to smaller scale filaments also. So you will see almost more complicated structures. But the key point is that the vorticity alignment to filaments is seen at seemingly every scale. Of course, the quantity of which and the size of the quadrants are scale dependent. So it's an important question to wonder which scales for vorticity are important for galaxy evolution. I'd say that way the vorticity can be computed on many, many scales. But what sets a scale for your studies is that you want to define the vorticity as the environment of the galaxies. The galaxies you are studying are not multi-scale. They are usually only within a range of scales. So if you're looking at the local environment of that, you have a lower limit scale on which you will be wanting to compute the vorticity anyway.
So you're sort of smoothing up to the largest scale of relevance in these regions. If you look at it as a map, does it really look like the filaments themselves are excluding vorticity?
Well, if you look at the map, I don't think I've included one in this presentation, but Yeah, but if you look at the filament in the simulation, you really see vorticity tubes whirling around filaments. So they whirl around. That's another effect, but they whirl around not too fast. So usually, well, when you project all the vorticity along a filament on a 2D plane, you don't completely lose the correlation. They don't whirl 360 degrees, but they do whirl a bit, yeah. But you clearly see those tubes for each quadrant around the filaments. That's a very clear feature in hydro simulations.
I have a question. Something that I'm having a difficulty wrapping my head around. So you say that in the beginning, when the galaxies are very small, then they align with the vorticity of the filament. And afterwards, you have these mergers. But these mergers are going to be random. So you have a random walk in the direction normal to the direction of motion. And it seems to me like if you merge enough of them, then the coherent term is going to dominate over the random term.
No, so the coherent term from the vorticity.
Each one of these galaxies is rotating in the same sense, right? So it carries some angular momentum.
Oh.
Small, I agree with comparison to the normal component, but this is coherent. So right, in the asymptotic limit, this is going to dominate.
No, because it's not very coherent. As you see, well, the thing is, if you remember the whole story, when you're in a vorticity quadrant, yes, it's dominant because the accretion is coherent. But when you grow in mass, you go closer to the spine of the filament, and you grow also bigger. Your halo is bigger. So that means you start to overlap quite a lot. Vorticity quadrants of opposed polarity. Okay, so that's what shuts down this term, actually. It's not relevant when you grow in mass. Because you could say the same thing. I mean, you might have less merger, but you still have mergers, even if you're more away from the filaments. It's just a matter of who's dominant at what point in your history. All right. So here is the theoretical background. And what I want to do in this talk is discuss a simultaneous detection I made in a recent paper. So detection both in simulation and in observation. And the idea of this study was to observe the signal in simulation and in observation doing exactly the same thing in both. That is, using the same filament extraction method with the same specificities, ensuring that I have roughly the same mass distribution for galaxies in my observational and my simulated sample, and using similar methods to measure the spins NV over sigma. And the reason that motivated this study is that you apparently have a lot of conflicting claims in observations and simulation. And I wanted to know if that had to do with the way things are performed in different studies. Yeah?
Just for clarity, is the regular motion of galaxies along the dome in the same direction as the spine of the filament?
Oh, well, on average, yes. The galaxy moves from the underdense region towards the filaments and then along the filaments towards the nodes. So that's why statistically mergers are more likely to have an orbital momentum that's that's orthogonal to the spine of the filament. It's statistical, of course. There's a lot of deviation from that. So let's focus first on the spin alignments in observations. So the observations I use are from the SAMI survey, which is an integral field spectroscopy survey performed on the AAT, so the Anglo-Australian telescope in Australia. So it's an integral field spectroscopic survey, which means that we use around 60 different fibers, a bundle of fibers, to extract spectra across the entire face of the galaxy. So basically you have pixels and you have a spectrum for each pixel, which means that you're basically able to map the kinematics of gas and stars across the face of the galaxies. So SAMI contains about 3,000 galaxies. It's not a massive statistical sample, but it's still a really good sample for integral field spectroscopy. And the good thing is those galaxies are found across the gamma fields. So gamma is a large spectroscopic surveys with very high completeness. And semi-galaxies are found across this field. So what we do is that for each galaxy, we have maps for the line of sight velocity, for the dispersion. We also have the surface density maps, of course. And what we do is that we extract the kinematic position angle from all the velocity maps. So here's a simple case where, as you can see, the kinematic axis, the axis extracted from speeds, is very well aligned with the photometric axis, which is basically the shape, the major axis. That's from surface density alone. So this is the ideal case, but what can be seen is that if you focus on more specific populations, you can actually have a lot of mismatch between spin and shape. And I'm not saying there's no correlation. There is actually a lot of correlation. But you still have a degree of mismatch that can be quite wide, and that really impacts your samples. It's particularly true for spheroids, because their photometric axis is not extremely well constrained. For slow rotators, you can have this effect too, and of course for compact structures because of resolution. And this is very important because those three populations, they're predicted to dominate the high mass signal. So if you're trying to identify those trends from shape only, you might be quite far from where you actually want to be. So that's the idea of using kinematics and strictly kinematics to do this study. So we have the position angles. So we have the spin. It's 90 degrees from that. Now we have to reconstruct the filaments. And as I said, semi-galaxies are found across gamma field. So it gives us about 300,000 galaxies in a very complete spectroscopic survey in a pale pink. And it's particularly useful to reconstruct the filaments. So the filaments are reconstructed with a disperse algorithm, which is a topological algorithm that identifies peaks and saddle points. Basically, I won't give you too much detail about this one in particular. I'm pretty sure some of you use it. But the idea is that it's a pretty robust estimator that focuses on topology rather than geometry. And what it gives you is that it correlates something called the persistence threshold, which is the level at which you want your detection. It can be correlated to a signal over noise threshold when you do that on a galaxy field.
How many R's do you
In different ways. So the main problem for that is that we don't have we have groups, we don't have too many clusters, and we're only doing things between 0 and 0.1, z equals 0 and z equals 0.13 because that's where the semi-galaxies are. So we don't have that many statistics for environments. So correcting the redshift space distortion per se is almost impossible. So what we do is that we try different methods and we check that we have the same results for each method. So the first one is do nothing. Pretend there's no redshift space distortion and look at the results that you have. In that case, what happens is that you get a spurious filament along the line of sight that are due to the groups that are stretched along the line of sight. The second method is remove all filaments that are along the line of sight and look at the results you have without taking into account those filaments. Which means that galaxies that would have been identified, those filaments, will be identified to filaments slightly further away, but that are more likely to be real. And the third method is remove both the filaments and the galaxies that should be assigned to them. So that means reduce your statistics, but make sure you're not at all perturbed by redshift space distortion. So I use those three methods and check that I'm not missing anything from one method to the other and that the results are not greatly impacted. One reason why I'm not impacted is because I don't do things in full 3D, right? The galaxies are assigned to their nearest filament in 3D, but then when I'm comparing the spin to the orientation, I do that on the celestial sphere, so it's projected. So you miss the component along the line of sight anyway, so that way you don't have to be too concerned about whether it's reliable or not. And this is why you can use any of the three methods and still get the same results. I'm guessing that if I were to do things in full 3D, I wouldn't be so lucky. So the key message is the spin flips, the spin tendency of being aligned on orthogonal to the filaments are recovered in the semi-surveys. So as I said, I compared 2D spin axis compared to 2D projected filaments on the celestial sphere. So I compared angle in 2D. And if I look at the PDF of the kinematic angle between the spin of the galaxy and the nearest filament, then I find a similar trend to what I found before. If I look at small mass galaxy, I have an excess of low angles, so an excess of alignment. And if I look at high mass galaxies, I have an excess of high angles, so angles close to 90 degrees, so an excess of orthogonal alignment. And for mid-range mass beams, I have mid-range results. Note that in this case, it's a 2D angle, so if you remember the 3D plot, the trend looked opposed because it was the cosine. And so in 2D, you use the angle. In 3D, you use the cosine. Because what you want to compare to is to a uniform distribution that is flat, because that's easy to compare to. All right. So we've seen that the flips are recovered. We want to be able to constrain the transition mass a bit more, the mass at which the orientation changes. And to do that, we compute the average angle across different mass beams in different ways. So the dashed lines are the results for each of the RSD, the redshift space distortion correction method. And this is a composite results. So what you see is that you do transition from lower angle at low mass to higher angle at high mass, and that the transition mass in that specific case is constrained around 10 to the 7, 10 to the 8 solar masses. To assess the significance of this estimation, what I did was compare the average angle in the sample that have stellar masses higher than the threshold to the average angle for galaxies that have masses lower than the threshold. And I varied the threshold quite a lot, like I did in the last plot, to find where I had the most reliable signal. And this is the point you get here. This is the signal. The blue contours, they are obtained, they estimate the noise, and they are obtained from random galaxy filament reassignment. And you resample that 100,000 of time, and that's the kind of contours we get. And those contours estimate the error on the signal, and they're basically bootstrap plus PA error resampling. What I can tell you from studying that is that actually the main source of error by far is the low statistics. After correcting for low resolution galaxies that were in cluster, etc., we are left with about 1,500 galaxies in this study, which is very low to estimate this kind of signal. So we have a lot of spread. Still, we're just above the 2 sigma detection threshold for this signal, for this pair of signal, which is about the best we could expect from this kind of sample. Something that I also had a look at was the scale effect on the transition mass. And by scale effect, I mean the scale of the filaments. Filaments are multi-scale in a sense, so you can compute them on a number of different scales. The good thing is gamma has quite a high number density of galaxies and is very complete, so you can actually try to identify different scales of filament. So here, I lowered the signal over noise threshold to 2 sigma, which means that I included a lot of finer filaments in the study. And what I find is that when I do that, the transition mass is actually decreased to 10 to the 10.1, 10 to the 10.2 solar masses. And the alignment signal gets fainter, but the orthogonal signal at high mass then get close to 3 sigma. So basically what happens is that when you go to finer filaments, the transition mass is lower, so you increase a lot your high mass sample. Most of your galaxies become high mass, and you've got a very clear high mass signal. But then you reduce your sample to very low mass galaxies, and that kind of reduces your low mass signal. So even with a sample like SAMI, we start to see the effect of the filament scale onto this transition, which tells you about the complexity of this process. It's actually very scale dependent.
So let's go back for a second to the sort of more general framework. So the way the filaments are being found is you unleash disperse on distribution, and the distribution has, in one way or another, even by denying neglect, taken up the RSD.
Yeah.
And so, well, first of all, I'm still a little surprised that RSD wouldn't have a big effect because of finger of God, etc.
So it's not that it doesn't. So just to be clear, it's not that it doesn't have a big effect. It does create spurious filament. It doesn't have a big effect of this signal because this signal is in 2D. So the component along the line of sight disappears.
No, I realize that, but you're also doing assignment. You're assigning things to filaments that you found and then project them.
Yeah. Yeah.
So there are a number of things that, well, I guess my general question is, you check this with simulation first.
Yeah, after I check this with simulation.
It all comes out. So you basically got some mocks of the whole pipeline you're putting it through, and you're showing that these identifications and the filaments that come out are that.
Well, we don't have a light cone big enough in simulation to do a strict comparison. So in a sense, we don't have RSD in simulations. So we don't need to correct for them. So it's not a strict comparison, but that's why we use 3 methods. One of them is not correcting for RSD, and the most extreme one is cutting out everything that could be impacted by RSD. And from that, because we have similar results, at least in both cases, and also on all intermediate case, we're pretty confident that the signal is there. So we don't try any fancy RSD correction because, well, that wouldn't be the most relevant thing in that sample. Because the RSD correction, like squishing the halos, that kind of thing, it works when you have a lot of statistics, but we don't have that many groups in here, so that wouldn't work. It's been done before in gamma when using the full gamma field. So we could have used that. But on such a small area in the gamma field, that wouldn't be efficient. So when you say correct, it's more like, look at what happens if we don't correct, and look at what happens if we get rid of everything that could be impacted. And then try some intermediate methods. And what I'm saying in that this signal is robust to all of these methods of doing things.
It's not so much that issue, it's whether it disperses coming up with the right stuff.
Well, that's why we decide to keep or not the stuff, right? We try believing disperse, knowing that if we don't do any correction, there will be spurious filament. And we're being very harsh to disperse and saying, I don't want anything along the line of sight. I don't believe that. So those are the two extremes, and with some intermediate tries as well. So this is the overall result in the simulation, in the integral field spectroscopy survey, to try to identify whether we were on the right track or not. I also did a comparison with a big hydro run called Horizon AGN, which is similar in a sense to Eagle and Illustris, except it's done with Ramses, which is an AMR code. It's 100 megaparsec per H on the side. It has kiloparsec resolution. It includes a lot of physics, all the basics, AGN, supernovae, type 1 and 2 star formation, etc., cooling. So what I did was create SAMI MOX in Horizon AGN. So MOX within a 1 effective radius for all galaxies above the resolution limit, which is a bit lower, higher in the simulation than in observations. In SAMI, we can go all the way down to 8.59 with reasonable resolution. In Horizon AGN, I have to stop at 9.5. Below that, I'm too unresolved to compute the spin. So we chose a 1.5 kiloparsec SPAC cell, and it's luminosity weighted. So it's designed to be the exact equivalent in a simulation to the SAMI data that we have. Here, for example, you have the line of sight velocity, dispersion, and surface density for high V over sigma galaxy, and here for slower rotator. So we did compare those MOX to SAMI observation and also to similar MOX done in the Eagle simulation in this paper. And I'll discuss about that later. For the filament extraction, we tried to extract filaments in the simulation that were as close to what we could get in gamma. And we tried to do that in two ways. First, we did use disperse, just like in observation. In simulation, you can do it two ways. You can extract it from the gas density field, so from a rather smooth field. Or you can extract it from the galaxy distribution, just like in observations. We did both. We tried to extract it from the gas, and in this case, we chose the persistent to fit the median intercritical point distance between gamma and the simulation. That is, filaments would be roughly the same size, would have roughly the same size, distribution size in gamma and in Horizon AGN. And we also extracted another network of filaments from the galaxy distribution directly, and with the same signal over noise threshold than in gamma. And here are the sets, one of such sets of filaments in Horizon AGN. In that case, those are the gas filaments. And we did recover at z equals 0 a similar signal in Horizon AGN. So this is similar to what we had before. Here you have the average angle for the sample of galaxies over mass threshold, and here the average angle for a sample of galaxies below the mass threshold. So what you want is that this one be aligned and this one be orthogonal. So you want to be in that quadrant, right? So for Horizon AGN, those are the red-orange contour. And the kind of noise that you can expect are the blue contours obtained from random galaxy filament reassignments, once again. And what you can see is that you do recover a signal whether you use the gas filaments or the galaxy filaments. Now, there are differences. Like the low mass signal is better constrained with galaxy filaments than with gas filaments, which is kind of expected. For the slow mass, you want to be able to probe small filaments that are relevant to galaxies, so that are traced by galaxies. So it's usually the best way to go. So you're in the right quadrant in both cases, and you're always above the 2.5 significance contour. Now, if you want to compare that with SAMI, those are the pink, green, and purple line. The signal is fainter than in SAMI. If you compare with the best SAMI signal we have, that is the signal obtained using all galaxies resolved in SAMI, so everything above 10 to the 9 solar masses, and choosing our best fit mass threshold. This is a pink contour, and here the center of the signal. This is the 1 sigma contour. Well, you have kind of a discrepancy. But then you have to realize that in horizon AGN, we can't go as low in mass. We're stuck at 9.5. So when we mock the SAMI sample in horizon AGN, we fit the mass function as best as we can, and we complete what's between 10 to the 9 and 10 to, what should be between 10 to the 9 and 10 to the 9.5 in SAMI, with things between 10 to the 9.5 and 10 to the 9.75. So we switch a little bit to a slightly higher range because we don't have too low mass galaxies. So because we have this limitation, if we impose this limitation in SAMI and we play around with the mass threshold, well, we do have the purple contour for SAMI, with the center of the signal being here. And well, errors are very large in SAMI because it's slow statistics and you have the PA errors. But overall, you have a reasonable match between horizon AGN and SAMI. To the level of error that we have, the two signals are consistent. I would still say that I find that there's a tension between the two. And that if we remove everything in SAMI, well, the tension is somewhat relieved, but the signal still seems to be a little bit fainter in horizon AGN. And it's actually something we can't really avoid because, well, we have some key limitations in horizon AGN, the first one being the resolution. So the precision of the spin orientation is limited at low mass in horizon AGN. We have puffy small disk. We don't have nice smooth thin disk. So because we do not resolve those thin disk, high V over sigma and high ellipses that are seen and that are everywhere in SAMI, where they are poorly recovered in horizon AGN. What you get, the equivalent of one of these guys in horizon AGN, is a puffy disk with a not so well resolved angular momentum. And this is really nicely seen on these plots. That's V of sigma over ellipticity. So the V sigma ellipticity plane. And all the dots are in SAMI. And the pink and black contours are horizon AGN. And this is the median in SAMI. So you can see that the trend is right, but that in horizon AGN, the high V over sigma part is clearly missing. We're saturated because of resolution. And another problem, of course, is that in horizon AGN, if you look at the galaxy mass function, you do overshoot the observed mass function at high and low mass. So the halo to galaxy mass ratio distribution is probably not fitted to what you would have in observations, which mean that you're not very realistic in the way you model galaxies at very low mass and at very high mass in simulations. The most important and the most constraining part, though, is this one, the resolution that tends to kill the low mass signal. So in horizon AGN, it's there, but it's significant, but it's still faint. While in SAMI, well, it was like incredibly easy to recover, given that the signal had been eluding even in a simulation for so long. Yeah. So those results, those findings, they are in line with some of the previous works that used the shape as a proxy for the spin, mostly in the SDSS. The first one was Temple et al. 2013, which compared the PDF of the cosine of the angle between spin and filament for some galaxies in the SDSS, and compared the trend for elliptical versus spiral galaxies, and did find a bit of a trend, but the trend is actually what's above the gray line, so it was still very ubiquitous. Well, it did find that these galaxies are more likely to display a minor axis parallel to filament, but it's a lot of proxy and it's a weak signal. And using shape in observation, it's quite difficult because ideally you would like the 3D shape, but it's actually quite hard to reconstruct with all the inclination degeneracy. So my work on kinematics is aligned with that and well, improves the significance quite a bit. But still, I wouldn't be honest if I didn't tell you that there seem to be quite a lot of conflicting, inconsistent claims in observations in simulation community about this kind of signals. And the rest of my presentation, I'd like to focus on those apparent issues. If you look at the literature on the subject of spin alignments in the cosmic web, if you look at the abstracts, you're going to find a lot of apparently inconsistent claims. You're going to find all spins orthogonal to filament, or spin orthogonal to filament, no transition detected, or no detection at all for any kind of spin alignment. That's a recent one. Or transition detected even if in a non-grid code, or transition detected in the SDSS from shape, as in Temple 2013. So how do we make sense of that? Some of these studies are even made in the same surveys. So that looks a bit problematic, but actually, if you look at the paper in details, and if you look at how things are done, you could quickly realize that most of the time, those claims are not inconsistent. They're just not focusing on the same thing. So to avoid having this wealth of claims that make no sense, I would strongly suggest to observers to really focus on a very key component of resolving the signal, and those things actually resolve most of the discrepancies. And the first key message I want to give you is that do not believe too strongly the expected mass transition from simulations. Why is that? Because you can have basically any mass transition that you want, depending on the scale of the filaments that you reconstruct. Filaments are multi-scale. Nobody reconstructs all the scales. Some reconstruct just one scale. Some finders reconstruct a range of scales, which doesn't mean everything in every scale. Everyone has their own mix depending on the finder and depending on the parameters used with the finder. And actually, the mass transition could be anything from 10 to the 9.5 to 10 to the 11, depending on how you tune your finder. So here's an example in Horizon AGN where in black you have filaments that are typical to the one that you would extract in gamma. So seemingly large-scale filaments because you don't have the same resolution in gamma as in hydro simulations. And in shades of orange are the filaments that people typically reconstruct in simulations for exactly the same studies. As you can see, this is not at all the same scales. And that explains most of the discrepancy between the mass function. Hence the importance of checking things for a given scale and on studying things on different scales if you can. So it's a tricky subject, but what I would suggest is that you don't get a prior too strong than this as a reasonable guesstimate when you're trying to find a transition in observations. Usually the filaments extracted from spectroscopic surveys range from 5 to 20 megaparsec in length, depending on how complete and how dense your sample is and how far in redshift you look at. And that basically means that you have a lot of latitude to choose different parameters, to choose different scales. And your mass threshold will be very unconstrained. Yeah?
So, you showed us earlier that different, so galaxies that grow next to filaments with different sizes would have different transition mass. So what sense does it make to find a universal transition mass? Wouldn't it make more sense to find the threshold mass as a function of the nearest, the size of the nearest filament?
Well, you can do both. The problem is that in observations, you can't recover all the filaments that you want.
You can do it in simulations, you can misunderstand.
Yeah, that's what we do in simulations. That's what we have this, and we can look.
So what scale do you find if the threshold mass is a function of the size of the nearest filament?
That's another complicated topic. How do you define the scale of a filament? You could choose its. Well, they're not all consistent. That's what I mean. It's actually a complicated issue. Would you rather look at the density, at the ratio between the density of critical points, at the thickness? There are many things, but the key point is that in any case, when you have a tracer of scale, you do have variations in the mass function, in the mass threshold, and that's actually also expected from theory. So if you want to know if we did that in simulation, yes, many people did. Like this is a good review of this. We do expect transition masses, and we do expect these spins to be scale dependent. Well, the phenomenon itself is multi-scale, but which masses correspond to which orientation is very scale dependent. So that's indeed expected in simulations, but you have very few reviews that state that clearly. And most of the simulator papers that you have on the subject, well, they focus on one scale because that's well resolved in the simulation, and why not? And they focus on what they find for their scale, but they don't spend too much time explaining how scale dependent it is. And in practice, it is a lot. Another related message is beware of your mass distribution. We're talking about a mass-dependent effect. So you can only cover transition masses that would sit at the middle of your mass distribution, right? And most of the claim that galaxies are oriented orthogonally to filaments in observation actually focus on rather resolved filaments and very high masses galaxies. So as you expect, you have an orientation that's orthogonal and you don't see anything that's parallel. Similarly, in this recent paper by Krolewski et al. In Manga, they claim to have a non-detection, but actually what they do is that they mix all the masses. So their non-detection is mixing all masses from 9 to 10 to the 9 to 10 to 11.5 solar masses, looking at the average angle and saying there is no detection. Well, you're mixing the two trends, and you have a transition mass that's right in the middle of that. So if you're mixing the two, of course, you don't find any signal. So you must really be careful when you have a certain mass distribution. This is the one in SAMI for those all galaxies and those that have resolved kinematic parameters such as V over sigma. And this is the 2 sigma filament transition range that I have in my study, and the 3 sigma. So as you can see, you have to think about adapting the scale of filaments you're resolving to the masses you resolve. And that's very, very important. If you get all your galaxy here, you see no trend. If you mix all those galaxies into, and just do the PDF for all this all together, you don't find anything either. And the last important piece of advice is to preserve the morphological diversity in your mass bins. What some papers suggest, and in particular Cody's 2018, is that alignments are driven by fast rotators at low mass and slow rotators at high mass. And this is related to the mechanism that gave rise to those populations in the first place. You're talking diffuse accretion at low mass, so you're likely to form disks, and mergers at high mass. So you expect a bigger population of slow rotators in the mix. And this one, slow rotators at high mass, is very important in integral field spectroscopy because in this kind of surveys, you are worrying about whether your position angle is well resolved. And cases where it can be not so well resolved is when you have slow rotators, even at high mass. So there's a tendency in IFS studies to be very, very strict about how well you want your position angle to be resolved. And this leads to basically depriving the high mass sample of any slow rotator. And in that case, well, this is the average cosine of the angle, stellar mass. In that case, you don't really get exactly what you want, but that you have the opposite trend. You would like to be here and you're here. But that's expected because you got rid of the population that would have given that would have made most of the trend. So if you take those 3 points into account, you can actually explain most of the apparently conflicting claims I've been seeing in the literature in the past years. Now, where are we out in simulations? Then again, in simulations, again, there seems to be an apparent disagreement, but that is not as sharp as we claim it to be. What I can say is that in different types of simulations, we all see a transition for halos, but not with the same transition mass. Once again, this is related to the scale dependence. It depends on which scales you want to define your filaments on. And we all see a transition from strongly orthogonal spins at high mass to at least random at lower masses, and sometimes to parallel at lower masses. So the disagreement is, does it become aligned at low mass? But I want to insist on that. If you look at the paper closely, even those that say we don't see a transition, what you see on their plot is a transition. It just doesn't go as far as aligned. But this is an example. So in Horizon AGN, Illustris, and Simba, 3 big hydro simulations using very different methods to compute the hydrodynamics, you do see the full trend going from orthogonal at high mass to parallel at low mass with a wealth of different transition mass. If you look in Eagle, in a paper that claims not to find a transition, well, you actually find a transition, but you reach your resolution limit before you can even see maybe a transition to alignment. And of course, this is directly related to the scales chosen by the finder. You can see that by looking at the alignments for halos. The transition mass for halos is extremely low. It's 1 deck smaller than the one in Horizon AGN, which tells you that from the start, the studies were doomed to disagree on the galaxy transition mass because they didn't choose the same scales for the filament in their study. And you actually, even in that case, you still find hits of a transition for gas disk. And in massive black, another comparison, it's a bit messier. Massive black 2 is maybe not the most constrained simulation in terms of baryon physics, but you still find hints of a trend that goes in the same directions. So I'm saying I don't have the impression that we disagree so much in simulations either. We have minor disagreements about the mass transition itself. Because of the different extractors we use, because of the different scales we choose to focus on. But other than that, we're still going in the same direction. And as I was mentioning earlier, beware of what you define at the scale of your filament, because you can do scale analysis, but the temptation would be to use density or thickness only to define whether you're in a small scale or large scale filaments. And actually, those two quantities vary along the filament from saddle point to node quite a lot. I mean, in similar amounts to variation across different scales. And so do tides. We saw that at the beginning. Tides vary along the filaments. So when you're using those two, you're not really probing different scales of filament. You're also probing different locations in the filament. So yeah, it's the hidden complexity explains a lot of the discrepancies. So what I would suggest for people who use disperse is to define the strength of a filament through either its length or the ratio between the density at the saddle point and the density at the node. Yeah, I think I'll stop here. So in conclusions, we recover a spin alignment transition at z equals 0 in an integral field spectroscopy survey and in big hydrodynamical simulations simultaneously with exactly the same method in both cases. We find hints of a dependence of the mass transition on filament scale, which is expected from theory and simulation. And we suggest that extra care should be taken when considering mass and morphology sampling in observations. And I'd like to point out as well that simulations are starting to agree a lot more than they claim on the existence of these trends. And that what we should focus on is our tinier disagreements that have a lot to do with the baryon physics and the subgrid model we use, actually. Thank you very much.
Shift this question slightly. What is understood about how the orbits of work companions of the galaxy, nearby
So,
neighbors of the galaxy, correlate with this?
sorry, I couldn't hear you properly.
What is known understood about how the orbits of dwarf companions of the galaxy,
But the companions of the galaxy?
dwarf companions of the galaxy, correlate with its spin? If you
The
have
dwarf-
large-scale conservation of angular momentum from the collapse of material controlment, I would think that the stuff that doesn't get incorporated into a disk would also
In dwarfs.
tend to orbit in the same sense.
Sure. So we find hints of that in simulations. However, in most big hydro runs like this, we are too unresolved at dwarf scales to really think anything about the dwarfs.
And it's very hard to measure, I would assume.
Oh, it's hard to measure, but it's doable. In a paper I published in 2018, I was looking actually at the evolution of satellites around centrals compared to filaments in particular, and also to the shape of the halo. And you do recover, well, you have a complex interplay of all those alignments. The alignments with the filament, which is also the direction of stretching of the halo, and the alignment with the central, which, depending on how massive the central is, can be the same or not the same as the filament. So you have a complex interplay, and you find hints of satellites following the filament and then progressively reorienting with the central if the central is not aligned to the filament, or being very aligned with the central if everything is aligned. But I wouldn't say that it definitely is, it gives you a definite answer for dwarfs, because in essence we don't have dwarfs in the simulation. So we look for all satellites down to 10 to the 9, 10 to the 8.5 solar masses if we are not interested in their intrinsic angular momentum. But that's it. We don't go below that. So we are on our way to have much more resolved simulation that are still cosmological, although smaller. It's more of this around 20 megaparsec than 100 megaparsec. But we do have those simulations that are progressively running to the equal 0 and that have dwarfs. And we can see if what we claim for seemingly bigger satellites is still valid for dwarfs.
Any more questions? Or if not, let's send the speaker again.